hold a kind of research chair in combinatorics and quantum field theory, University of Waterloo. They did PhD at Boston University, their primer, and their awards include the Hubble Fellowship in 2016, and they've authored several books and 2 books, several articles. We take this from aujourd'hui on essaie d'avoir Karen Yeats, qui est un mathématicien canadien, et il est titulaire de la chaire de recherche du Canada de combinatoire et théorie des quantités de champ à l'Université de Waterloo. Karen fait son doctorat à Boston University avec Bill Primer, et c'est pris un peu le Hubble Fellowship en 2016, et il a plus un article de livre et aujourd'hui on va exposer intitulé Combinatorics and CSMQ.
Thank you very much. Thank you very much for inviting me. Anyone who was at FIPSAC has this talk before or something very close to it. You'll notice you heard combinatorics and quantum field theory, and the bulk of what I do my whole career has been combinatorics and quantum field theory, and that's kind of on this side of the picture here. But that's not actually what I'm going to talk about today. I'm going to talk about combinatorics as it shows up in Causal set theory, which is over on the other side of the page, which is something that I've become interested in recently. Although I guess recently isn't quite so recent anymore. It's something like 5 years now, a bit more maybe. And that's actually where we're going to start here. So one day I was sitting in a quantum gravity talk that ended up being a poset talk. And you know, that's not what you expect when you go sit down in a quantum gravity talk. And so that was sort of interesting. And this was actually a little bit before COVID. So it's actually been a while now, but okay, it still feels kind of recent because I don't think those COVID years actually happened. They're just sort of like, look at this continuity anyway. So what is the idea here? The idea is here, I'm going to draw my pictures with 1 dimension of space and 1 dimension of time here. And you got to imagine that you're here in the middle, and there are relative to your coordinate axes, there's points out in the world, you know, things that are happening. And maybe you have a friend, and your friend is on a spaceship, and they're on one of these spaceships that's traveling close to the speed of light. Right? And so this is like, you know, the old thing that happens in the science fiction stories where your friend is on the spaceship and they're going close to the speed of light and they go all the way over here, and then eventually they turn around and they come back, and everyone that they ever knew is now dead. Right? That's what happens in the story, right? When you're on a spaceship going close to the speed of light. And so that's what's going on in this picture, because say here's your friend is going, you know, pretty fast here and has at a constant velocity, and so there's a different frame of reference, and then the time axis has been flipped, sort of switched, sort of skewed in for them as well. And so if you have some point, you can see why this happens. So here's some point, and if I put this point in my coordinate axes, I get something like this. But if I put this point in my friend's coordinate axis, actually I'm parallel to these things. So it goes down here to end up on there, and then this other one's going to go down here to end up on here. And you can see the time dilation there, right? Because this little distance is much shorter than that little distance. And so that's why I don't get to hear these cool stories from all the cool places that my friend went that close to the speed of light, because I'm dead. I then gave a talk. This is the 3rd version of this, the first one, the FIPSAC one, but I also gave one in the technical program in Waterloo recently, well, on Halloween, in fact. So it's a good day to talk about it. Okay, so I'm going to use the kind of coordinates that you usually use in the proof, where we actually speed of light is kind of built in here, because what you remember from your science fiction knowledge, you don't have to have actual physics knowledge. It's a little bit of science fiction knowledge to understand this talk, because the only thing you really need to know, other than that everybody's dead after your friend's been on the spaceship, is that nothing goes faster than the speed of light, and then the speed of light is constant for everyone. And why is that? Well, because the speed of light here with these units is here at 45 degrees. So here's that's the speed of light. And we're going to call that's the light cone relative to my position. And the reason you want to think of it, like, why is it a cone? Well, because if there were 2 dimensions of space here at one of time, it would be a cone. And So the other thing we want to remember is what I just said, that nothing, not even information, can travel faster than the speed of light. And so if I want to cause some effect on some other point here in this space-time diagram, it's got to be inside my forward light. So that's like the only way I can affect anything. It has to be like, at the very least, the information for me has to have gone there, right? Otherwise, I cannot possibly affect it. So it has to be inside here, speed of light or better. Okay, so let's put some points in here and think about where they are. So if something's inside here, this is something that I could have a causal effect on, and I'm gonna treat that here by just putting a line between them, because there's a causal relation. Everything here on the inside, on the top here, this is stuff that's in my future. This is stuff that's in my past. All the things that are out here, outside of the light, these are things that relative to me are space-like. And why do we say they're space-like? Because any point out there, there's some choice of coordinate axes so that they're just separated by space, right? They're just purely space-like separated. Everything up here, inside or at the bottom of inside the bottom or the top, is time-like separated here or in here. And the things that are literally on the light cone relative to me are lightless. All right? And so now, so you're sitting in this quantum gravity talk, and there's a space-time diagram, fine. Okay, but we want to abstract away, and the only thing we're going to keep is this causal relation. So I'm going to draw the light cone again for me. So here's me, I'm in the center here. And now I'm only keeping a causal relation. So maybe here's something that's above me here. And now this guy itself has a chord and a reverse light cone. And so if I have some other point, if it's say out here, well, that's causally related to me, but not to this other point, right? That's outside of that point's light. And if I put something up here, well, that would be maybe inside both of their light. Down here, maybe I've got something like this, and something here, you know, etc. So what you're left with is a poset. And well, I mean, you have a poset and you just have some Minkowski space, but we want something else. We want some kind of finiteness. And the kind of finiteness we want is we want it to be locally finite. Okay, now, in case you haven't thought about posets in a while, let me just remind you of some basic poset language. And while we're at it, we can talk about how you would say the same things in causal set. Okay? Because a causal set is just a poset as a model of space. A locally finite poset. So I wrote down your poset axioms. I'm going to write my posets with a less than or equal to. You might first write them the other way. It all comes down to the same thing. The interval is given a top and a bottom, or a bottom and a top element. It's the set of all the things that are between in the poset. And a poset is locally finite if all the intervals are finite. All right, and in that case, we'll say it's a causal set. Causal set just is a locally finite poset. It's just another word for locally finite poset. But we have some sort of physics language that we will tend to use. So it's going to be pretty important to talk about the upset and downset generated by particular elements. So the upset generated by an element is all the things that are above that element, and the downset generated by an element is all the things that are below that element. See, this is why I like this. You might have heard these called ideals and filters, and I have to say I never remember which one is which, so I like saying upset and downset. But in some ways, the this language is even more evocative because the downset generated by some element is just the past of that element, and the upset generated by the element is the future of that element. So that's also easier to remember than ideal and filter. All right, everyone good with poset basics? Now there's one more thing that we need. One more piece of information, and that is that we want the number of points in an interval in the causal set to correspond in some sense to the volume of the continuum space-time interval that it would correspond to. And this is this number to volume correspondence. And so, well, I pose this as a question, but the sort of idea of causal set theory is that maybe that's all you need. All right, I was slightly more dubious. I posted this question: could this be all that we need in order to build theory of space-time, we build a quantum gravity theory. And well, there's two ways to think about this. One is, well, maybe it really is. And the best piece of evidence that it really is that, well, and I wrote this very vaguely, but for suitably nice continuous spacetimes, it is. So there's a theorem of Hawking-King-McCarthy element, two slightly different versions, a year or so apart, that say, yeah, if you start with some Lorentzian manifold with suitable niceness that I don't want to get into, and you also have the volume element, then that is in fact enough to reconstruct the manifold. Okay, now this is one of these physics theorems. It's a little hard to pin down exactly the conditions, but it certainly in suitably nice cases holds. And so that's very suggestive that maybe this really is enough information if we want to discretize, then up to the discreteness scale, maybe the causal set plus this number volume relation, which is why you want it to be looking finite, maybe this really is giving us that. Now, the other perspective you could take is that even if maybe it's not enough, it should at least be the causal set. And so Raphael Sorkin in '91 wrote a paper about forks in the road, which makes the argument that if you want to take seriously the idea that your quantum gravity theory should be Lorentz, then it should be discrete, which, okay, we're trying to discretize stuff, and I'm a discrete mathematician, so I want to discretize stuff. Once that's discrete. And then we take seriously the path integral, then you're brought to causal sets. Now, it could be that you also need to add in more, but those are pretty basic physical axioms. So I would like to argue that even if you do need to add something else in, at least the causal set should be there. Okay. And so then, again, I phrased it as a question instead of maybe a slightly more positive, more forceful way. But what you want is that if the causal set's somehow manifold-like in some way that's not fully precise, then up to the discreteness scale, it should determine the math in some suitable sense. This is sometimes called the Helpfer-Mouton of causal set theory. And there's not even a completely rigorous statement on it, but it is very motivating to a lot of what people do in this area. And this is where I want to point out that if you're going to the physics garden party, you're not really going to impress a lot of people with your causal set knowledge. It's a bit of a niche approach to quantum gravity. But I think it's a very appealing approach from a mathematician's perspective, partly because locally finite posets. But from a physics perspective, I think it's also, I mean, it should be Lorentzian, right? Like a lot of theories of quantum gravity are Euclidean, but I mean, the world's not, right? Like space is all fine and good, and time is really kind of different. And so I think we want to take seriously the idea that space-time should be Lorentzian. And likewise, I tend to think we want to take seriously the path integral and discreteness. So I think there are real physical reasons why it's a good idea, even though you're not going to impress your physics friends at the physics garden party, because it is a bit niche. Fine, that was all vague, blah blah, right? So what do we concretely do, right? Like, let's do something. Let's not just like blah 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 all day. So what are some things we can concretely do? And I'm basically going to spend the rest of this talk talking about some such things. So one of the things you might want to do if you're trying to investigate causal set theory is you might want to look at poset invariants that have physical analogs. Or you might want to take physics, like things that you want your spacetime to have, and you might want to try to find some poset invariant that corresponds. And so, for instance, one of the simplest things that you might want, if you have, let's take it in a space-time integral, say you take the height of that, which is the length of the longest chain, and that becomes a notion of geodesic distance. So that's good, right? Geodesic distance is a good thing to have. Here's another thing that we can try to do. And let's take a finite causal set for the moment. You can think of it just an interval if you're working in a larger causal set that's not finite. And you could enumerate for every element in the causal set, you could make a pair, where the pair is the size of its past and the size of its future. And that gives you a poset invariant. Not one that I believe has really been studied from a pure math perspective, but one that, at least from some experimentation of Raphael Sorkin, who defined this, and some variants, seemed like maybe it's seeing something about this notion of manifoldness, in the sense that you can just do some computational experiments, and if you have posets that came from the same manifold, they will tend to cluster together based on this invariant and not otherwise. And I have there's some work in progress with a student of mine, Ian George, who's thinking about this and the next thing together, as well as maybe he had some undergrad students that were thinking about this, which he did. What's another thing you might do in a similar direction, sort of taking a bit of an enumerative approach here, is you think, well, what about a generating series of interval sizes? And you could ask, well, what kind, I mean, I can do that, right? I got a finite poset, I can make, well, it's finite, so I can make a generating polynomial of the sizes of the different intervals, and what does that tell me? Well, so Sumatri Surya, who's a physicist, and did some work that if the poset came from a Minkowski space, then you know exactly what these are, and it's dimension dependent. So you can actually read the dimension of. And in fact, you get some nice binomial coefficients. It's actually fairly pretty. And when I say dimension, this is one thing I want to be careful about. The kind of dimension that matters to me is the Minkowski dimension. So what dimension of Minkowski space can you embed this poset in, which is different from the order dimension once you get past 2 dimensions. It agrees with order dimension 2, but after that. And this is again something that my student Ian and I are thinking about, because yeah, generating series are nice, and you can try to do your standard generating functionality, and you say, oh, what sort of poset operations are nice with respect to this generating series and things like that. And so, for instance, one of our fairly new results that's hopefully going to be out in a paper fairly soon, is that you can distinguish and reconstruct series parallelisms. This question of looking for estimators of the Minkowski dimension is something that people have thought about for a long time, and not for a relatively long time. Not just Sumatri's work on the integral sizes. There's many examples, and the first one I would say is this one from 1978, which looks at the number of relations scaled by the size of the poset. So that's something that, with some caveats that I don't want to get into for the purpose of the colloquium, also gives you the Minkowski dimension. So it depends only on the Minkowski dimension. Yes.
And so that for any poset, you define Minkowski dimension, like put it.
No, the statements are always the other way around. They're always, if you got this from a Minkowski space, then this will give you the Minkowski dimension. And now you could use any one of these to define some notion, but whether or not it tells you what you want to know, then it's the question. But I keep talking about posets that came from a Minkowski space. What the heck does that even mean? So this is another direction that people in the causal set world, physicists in the causal set world, investigate, pursue. And this is what they usually want to mean. So you're going to take a Lorentzian manifold. And now remember, what did we say? We said that the number of points in an interval in the causal set is supposed to line up with the volume of the space-time interval. So let's just plunk down some points so that happens, which means we want to do it by a Poisson distribution, or at least that's the most natural thing, is to do it by a Poisson distribution. Yes?
So what is a Minkowski space?
So a Minkowski space is a flat Lorentzian manifold. So basically Rn, but instead of using the usual metric, you use a pseudometric where you have signature where one of them is plus and the other ones are all minus, or vice versa. I don't really care. And then a general Lorentzian manifold would similarly have a Lorentzian pseudometric. And notice that it's very important for this whole story that there's one time dimension, because that's what gives us the causal relation. And so, sometimes you might do a change of variables and you get 2 time and 2 space, and that's going to have a very different behavior from this perspective. Similarly, if you ring rotate into Euclidean, again, you've lost the Lorentzianness. And some of this is a story that says Lorentzianness is important, which again, I think is a very plausible axiom perspective of sitting here in the real world with time being what it is. And that answer your question?
Yes.
Okay, so this is what you're gonna do. You're gonna just choose points by a Poisson distribution on a Lorentzian manifold and then use the induced causal order. And then precisely what's going to end up happening, the probability that there are m poset elements in volume B is going to be given by this little Poisson type thing, where you've got this density parameter rho that's determining how densely you sprinkle your points. It's called sprinklings. So lots of people have studied these sort of random posets. The standard names that you would expect from this sort of probabilistic mathematics have looked at this. There's just a couple of them and many more. And there are lots of connections to things you know. So this first one's a little bit cheap, but it's a good one because it's one I can explain just in the context of the colloquium. So the height of a random two-dimensional causal set is just the longest increasing subsequence in a random permutation. That's actually easy to see. I sort of mentioned briefly that in 2 dimensions, the Minkowski dimension and the order dimension agree. And so then a random 2D causal set that is sprinkling on a flat 2-dimensional Minkowski space. And so that's the same as taking a random order dimension 2 poset. But order dimension 2 means there are 2 linear orders and you're taking their intersection. Well, without loss of generality, one of them is the identity, the other one is the random permutation. And so that if you just trace through what that means, that's exactly this. And other things, it's on from there. These smart probabilistic combinatorics people have studied these things. Okay, so I want to combine those two things together for a moment, because I said, well, I would like to have the kind of things that I want from a space-time, like I want my space-time to have. And one of the ways I can try to see if I made the right choice is by seeing if it works out on these sprinklings. And so a concrete example that I've done a small amount of work on, although the bulk of the work is by physicists that are not me, is to look at the analog of the Dall-Inversion. Now, if you are like me, you do not remember what the Dall-Inversion is. It's sometimes called a box operator. Box. And what is it? It's the partials, the d by d variable square partials. So if I'm in 3 dimensions of space-time, like the world we are sitting in right now, I have something like this. But now the signs need to follow the Minkowski sign. So I don't actually care if you make this one plus and the other's minus, or the first one minus and the other's plus. But the point is the time has the opposite sign to the others. So it's like a Laplace operator, but it's got the Minkowski signature. Okay? And it should not surprise you too much that that's an important operator if you're in a Lorentzian map. Okay, so you'd like an analog on causal sets. All right. And so you say, okay, this doesn't seem so bad. I've got a differential operator. And differential operators, when I move to a discrete context, I say, well, a differential operator should probably be a difference operator, right? Okay, sounds good. But there's a problem. Because I said my posets were locally finite, they're not necessarily finite. And in fact, I don't expect them to be finite. Here's the reason. So let's say here's a point. And let's take a cover on this point. So let's just suppose that's a cover in my causal set. Now, this guy also has a 4 light cones. And notice this area here, what's this? This is the stuff that's not in the future of my green point here, also not in the past. Draw the past light cone, but started my highlighting sort of straight down there. So it's not in the past or the future of that upper point, but it is in the future of the lower point. Right? So this would be something that's incomparable to the top guy, but above the lower guy. And we said that the volume was proportional to number. And this has infinite volume if you keep going, right? So there's got to be a point in there somewhere. And wherever that, somewhere of all the points in there is going to be one that covers this guy. All right, but the same holds for this one, right? Like, okay. And it's still the case that this little strip here, if you go out far enough, I have infinite volume, so there should still be a point in there somewhere. Maybe you gotta go further up. There should be a point in there. And that same thing is going to be true forever, right? As long as you're not on the light cone of the original guy, then somewhere up there you should expect to have a light cone. And so it's not just that our posets are locally finite, so it could be the case that something has an infinite number of covers. We really expect that typically, if it's looking somewhat like flat space, we expect to have that many covers. And this is going to cause us trouble if we want to have a difference on it, right? Because, well, you could start with the finite context, and then you could take some sort of sum over covers, but you don't expect it to behave nicely when you take a limit, or if you're starting with an infinite one, you don't, that's not going to be well behaved. So you don't expect it to be well behaved. So that's not nice to expect. Okay, but Raphael Sorkin actually told us in 2009 how to fix this, and the answer is to use a suitable alternating sum. So we sum over all the covers, but then subtract off a suitable multiple of all the tops at intervals of size 3, I guess. So little chains of things, and then so Raphael explained how to do it in 2 dimensions. And then Bennikamp and Dowker in 2010 explained how to do it in 4 dimensions, and it actually works in all dimensions. And those are results of Faye Dowker and Field Glacier. There's 2 parts of it. And by saying this is the derivation, what do I mean? What I mean is, if you obtain this thing from sprinkling on a flat Minkowski space, then the limit will give you the density, the limit as the density goes to infinity will in fact give you the box operator on that Minkowski space. So that's the sense in which it is the right answer. Okay, now I said there was some alternating sum where you add on the number of covers and you subtract off some suitable multiple of the guys that are 1 step up, and then subtract off potentially the intervals of size 4 and so on. So what are the coefficients? Because this is another thing where you're a combinatorics person and you're sitting in physics 5, and all of a sudden there's a table of integers. Okay, well, they aren't quite integers, but like those denominators are not a problem, right? And they're not quite positive integers, but the signs are also clearly not a problem, right? So these have to count something, right? And yeah, so you're sitting in a physics 5 and you're like, oh, I don't know what's going on, and then you see a table of things that count something. And sure enough, it does. So that's my tiny contribution to this little thing, is I can tell you something that counts. So Lil Glacier gave a formula for each of these as an alternating sum of some binomial coefficients and some ratios of gammas that, if everything is even, end up themselves being binomial coefficients, and if not, they end up being, well, the thing you get when you get gammas with halves. So you basically get some odd factorials. So you just gotta take your favorite thing that can be counted by binomial coefficients or odd analogs of them, and well, there's still something to do because you have an alternating sum, so you need to figure out how to explicitly put the things inside, like to make the inclusions of sets work out so that you can actually do the enumeration. But you can do it, yes.
So the tables of what's D and C?
Oh, D is the dimension. And this table, I mean, you can calculate as far as you like. So yes, D is the dimension. And these are the coefficients. So this is coefficient of, I think this is the coefficient of the covers. No, this is the coefficient of just, well, it's the coefficient of covers and elements of size, intervals of size 2, intervals of size 3, intervals of size 4, etc. There's an offset in the indexing, and I'm not remembering exactly which one it is. So maybe this is coefficient of intervals of size. I think this might be size 2, and then similarly of size 3, similarly of size 4, but it's possible the offset, it's possible these are the intervals of size. No, I'm pretty sure it's not one, I'm pretty sure there's at least an offset. So they're the different coefficients, as I said, you have to give an alternating sum over intervals of different sizes to make something that's going to converge to your box objects. Okay, good. So if you want to see the first thing I found that works, that'll give you a combinatorial interpretation of these. Give you a picture. Something I rather like. So you need something that's going to be, basically you need some Catalan pieces. And you need to glue together some Catalan pieces in a suitable way. So I don't know what your favorite Catalan object is, but, well, I have a lot of, I like Catalan objects, but one of my favorites, because I also really quite like chord diagrams, so I'm going to use non-crossing chord diagrams. And so what do you need to do to make these things? Well, you need a sequence of, you need a cyclic thing of your Catalan objects, and you need a few extra bells and whistles. I want to bicolor my Catalan pieces. So some of them might have a blue outer arc, and some of them might have, well, this color used to be red, but I've got a colorblind safe palette now, and the red turned into orange. So something like that. They don't have to alternate or anything. I just made them alternate because that was fun for a little while. So I'm going to stop that. Something like this. And inside each one of these, you got to put an honest to goodness Catalan thing inside. So that. Don't have any choices there. We'll do this one here. Something like that. All right. This is going to be rooted. So pick the first vertex. And then I need one more piece of information, because one of the things I'm going to do in order to embed the smaller ones into the bigger ones suitably, to actually make, to instantiate the alternating sum that gives each of these numbers, is I need to keep track of some insertion places for each Catalan block. And the number of insertion places is going to depend on how big the Catalan block is. So this one is size 3, so I want to add 3 insertion places here. This one's size 2, so there's only 2 here. This one's size 1, only 1 here. 2 here. 1 here. 2 here. 3 here. And 1 there. And the way you then do the explicit inclusion is you insert groups of just bare vertices that don't have any chords on them into those places. And the reason you have different numbers of insertion places is because that's giving you the number of ways to insert little pieces. You put it all together, and then some of these diagrams with suitable constraints on how many unused blocks there are before various of the chords will give you something that's counted by these numbers. So, no, it's not the only choice. You could probably make something work, whatever your favorite Catalan object is. But something like this will do the job. So I thought that was fun. Okay, but if you were sitting here being really dubious about the last bit of this story, one of the things you might have been really dubious. Here we kept talking about, oh, let's say we sprinkled on a manifold. But look, if I want to claim this is going to be a fundamental theory of quantum gravity, I don't get to start with the continuum manifold, right? Like it should arise out of the theory somehow. So I really don't want to start with a manifold, not ultimately anyway. You know, I might stuck with that and definitely make progress and think about it using tools for you too, but that's not what you want in the long term. You want to be able to build your space-time. Ideally, you'd like to be able to reconstruct the 4 dimensions of space-time. Okay, we don't have that. So, you know, you'd like to have some way of building your space-time. And so the very first thing you might want to do is you might say, look, let's just take a poset of size n uniformly at n. Now, that doesn't end up being a very good way to get a space-time. And here's why. So there's a result of Kleitman and Rothschild, we're two mathematicians, that says if you do that, this is what dominates. So half of the elements are going to go in the middle. A quarter of them are going to go on the top. A quarter of them are going to go on the bottom. And then you have a 1/2 probability of any connection between them. in between each of the levels. So that's what ends up dominating just a random poset of size n. A uniform at random poset of size n. And just look at this for a moment. This is not a very good model of space-time. There are only 3 times, right? Like if this is now, this was then, and this is the future. That's it. And I mean, that's like not what our world is like. Okay. Now, and I think this actually, to some extent, is why you're not going to impress the physicists at the garden party. Because I think a certain number of people said, oh, well, so this is a stupid idea. But that's pretty glib. Just because I don't want to take my poset uniformly at random doesn't mean that there's not some very sensible way to take a poset, and expect to get something that is more like. So, in fact, one of the messages I want to give you is if you as a mathematician have some favorite way to generate that posets come up for you, or some favorite distribution on posets, why don't you take a look at what gets generated and say, would these ones make good space-time? Because a good process to generate space-time-like, manifold-like posets would be a really nice addition to causal set theory. And I think lots of us out there work with posets and have various either random processes on posets or distributions on posets. And maybe you have the right ones already in your vocabulary. And at the least, you could write a fun physics paper about just analyzing to what extent they are or are not good models of space-time. Okay, well, I'm going to tell you about another way that you could try to make them, and one way that people do study. And this is sometimes thought of as a dynamical model of space-time, where you grow them one element at a time. And so that looks something like this. So we're going to start down here. We got an element. And what we're going to do now is we're going to add a new element. And the new element is always going to be a maximum. So there's 2 ways I could do that. I could either put the new element so that it's incomparable with the previous one, or I could put it so that it's comparable to the previous one. So these are the 2 things. And I'm going to make this happen with different probability. I'm going to fix P. And this way it's going to happen with probability P. And so then this way it has to happen with probability Q, which is 1 minus. Well, let's go up to the next level. So what can happen here? There's some things that could happen. I could have something like this, where it's incomparable with everything. I could have something like this, where it goes on top of both of them. I could have something like this, where it goes on top of this one. I could have kind of the other version of that, where it goes on top of the other one. Did I miss anything? No, the same thing. You should correct me if I did. What else could happen here? Well, here, I could have it be incomparable with everything. I could have it be comparable to that one, above the one, but incomparable to 2. Or I could have this. All right, and now what's the rule for what the probabilities are? In each case, I picked some subset of the elements that were already there, and I said I'm going to put a new element on top of those ones. Okay, so we're going to have P to the power of the size of what I put it on top of, and then Q to the power of all the stuff I didn't put it on top of. So here, this guy is going to be just a Q squared, because I didn't put it on top of it. This one here would be a P squared, because I put it on top of both. These ones here would both be PQ. I think this would be clearer if I used a different color, because then it would not look like then the 2's and the labels would not look the same. Okay, and I am going to keep doing this because something interesting will happen at the end. Think ahead of what the interesting thing might be, because this is incomparable to 2 of them, so it's Q squared. This is comparable to 1 and not the other, so that's Q. But here in this last case, something interesting happened, because I'm going to take a subset, and that's going to be the things that I put the new guy on top of, but I want a poset. So I also have to take the transitive closure. which means there's two ways for this last guy to happen. Either I could have taken just 2 as my subset, and that would give me a PQ, so on top of 2 is not big.
Because your iPad is disconnected from the screen or something, because it's not in the last couple of.
I mean, I'm not connected to the screen directly, I was supposed to connect through Zoom. So the Zoom has done something stupid. That's not good. It's always hard to know what Zoom's doing. Oh, I know what it is. I somehow paused the screen share. How do I undo that? Oh, here we go. There. Fix. Apologies. Fix. It was me being stupid all along. I somehow hit pause by accident. Okay, there it is. All right. Now, sorry, small technical error, but it's fixed. Okay, so I said if I took just the 2, I get a PQ because I put it on top of the 2, not on top of the 1, and the 1 just came in for free for the transit closure. If I pick the 1 and the 2, then I would get a P squared. Now, but P plus Q is 1, so this is just P. So that's how it ends up working. So in the causal set literature, and of course, in the causal set literature, this is known as transit percolation. But it's actually something that was also known in the probabilistic graph theory world, probabilistic combinatorics world, because this is also a random graph. Now, what is a random graph order? Take the Erdős-Rényi random graph, put an order on the vertices, and now get an order out of that. Make the edges directed according to smaller vertex to larger vertex, and take the transitive quotient. That gives you a model for random posets. It's clearly not uniformly at random, so here's another model of uniform posets. And this is a model that, look, I put a whole bunch of names of people who are important in probabilistic combinatorics, and they have looked at random graph order. And then I also included one of my colleagues. So a couple of years ago, we had a causal set learning seminar, and Jane got interested in some of this, and she's done some work now on random graph order. And now again, you said, look, up here, we wouldn't really like the Clayton-Rothschild guys because they only had 3 times. There's a lot of space, right? Space is large and time is like really not very good. And unfortunately, these tend to go the other way. They tend to be too narrow. Time is good, but there's not a lot of space. And in particular, something that happens a fair bit is you get what the causal set theory is called hosts, which is just an element that's comparable to everything else. Now, that could happen in a model of cosmology. That's like when you have a new big crunch and then a new big bang afterward, because that one point there is comparable. Everything's either in its future or its past. So, could happen depending on your model of cosmology, but not too often, where it's just like everything's just too narrow. And this is where the graph perspective really helps, because from a transit percolation perspective, where you're adding the new elements one at a time, it doesn't make sense to have P depending on N. Because you kind of don't know what N is in advance, right? You're just like building it up one at a time. You don't have N, the final number of vertices. But when you think of it as a random graph order in terms of Erdős-Rényi random graph, that makes tons of sense to have P depend on N. People do that all the time in random graph theory. And that gives you a bunch of different regimes, and that's actually one of the things Jane looked at, is looking at these different regimes and how things like the number of posets, sort of qualitative facts about the posets that you get change over these different regimes. So it gives you some parameters to tweak to try to build something that's more like the spacetime that we see here. Now you can do other things that you can weight these things differently. I said we were weighting by the size of the subset that we chose, or P to that size. But if you put on your enumeration hat, you'd say, why does that have to be just P to some power? Couldn't I just have another variable like some T sub n instead of something like a T to the n? Sure enough, you can. And if you do that, you get something which the causal set people call classical sequential growth. And that's a nice set of models because you can also define them in a more axiomatic way. They satisfy an analog of Bell causality. They satisfy something called gregariousness, which is just that there's a non-zero probability of putting something that's incomparable to everything else. Why incomparable ought to be gregarious? You would have to ask them. And it also satisfies general covariance. And that's a point I want to get back to. Because general covariance, what that means in this case is basically if you take something like an observable, so like an infinite path through this process, then the labels don't end up mattering in the end. And that makes sense. Because here in the real world, like there's not labels on my space-time points, right? Like there just aren't labels. So really what we would like is something that's covariant throughout. I mean, we'd really like to be working with unlabeled posets. And notice that isn't actually what's happening here, right? They get a natural labeling from the growth process, because you're always adding a new maximal element. And in particular, you see 3 different copies of this poset that's a stick and a dot. So, it'd be nice to work with unlabeled posets. And, well, the first thing you might think is, okay, you take this up to isomorphism, right? You can do that. You get something. Pretty nice something, really. You get a poset of posets. Poset of posets by downside containment. Okay, not too bad. But you do lose something. You lose the fact that this is a tree. And if you want to use it in this kind of way where you're trying to compound in it and you're trying to do these sort of balancing arguments about these processes, it's really pretty nice to have a tree, not a other poset or other thing like that. And so the last thing I think I'm going to talk about, other than, oh, that happens when I touch that. No, bad. Okay. Okay. Well, now at least I know what my wrongs is. So if we want covariance throughout and we still want trees, then what you end up getting is something called cov tree. And let me show you how that works. If you were at the seminar this morning, which actually most of the audience was, you already know what cov tree is. So you can just nap for a moment. I'm going to do it. So I'm not going to go with the probabilities for now, but you can think of that anyway. And we want it to be unlabeled, so we're going to take off the labels. But now we're going to notice, what were the problem guys? The problem guys were these 3 in the middle. These guys were the problem because they were showing up on both sides. Because that poset has 2 different down sets of size unless it has the 2 dots, 2 dot antichain, and it has the 2 dot chain. And so what we're going to do now is we're going to upgrade all these things to sets. So these are going to be singleton sets. Those are all fine and good. I'm going to push these over because I need a little bit more space. So we'll push this over and we'll push these guys over and I guess put some new lines. So those were the ones that only had this guy. So that's good. And I'm going to push that guy over so that'll have this. I'm going to do the same thing on the other side. This one was okay, so I'll push that over there. And these 2 were okay. But now these ones were bad because they were both in there. And so the way I'm going to fix it is I'm going to now allow not just singletons, but also things like that. And now all of these copies, we can forget the labels and we say, okay, what's going on with this guy is it has both of those as downsets of size. And I can add other things here too. So for instance, up here, I can put something like this, which has still that. The downset over here, I can put something like this. I should get rid of these labels, which I do. And there'll be other things in here as well. It's not that every single element in there has to have both. So I could have something like that. That would be perfectly good, etc. Okay. And there's more. I have not drawn all by any means. And so on. And this ends up getting called cov tree. And if you were at the talk this morning, you would know that this leads to some other interesting problems. So for instance, here's the problem I talked about this morning. And I won't say anything about it other than to tell you what the problem is. So if you have k posets, unlabeled posets of size n, and there exists a q such that this thing, P1 to Pk, is set of downsets Q sides n, up to isomorphism, and is exactly that set, then we say that P1 to PK is a node of cup tree. And then what I talked about this morning is, can we find bounds on possible sizes of Q in terms of n and k? What can we say about the size of Q in terms of? And the answer is not all that much, but if you wanted to know, you should have come this morning. So you'd better go find a close time like curve and come back and go to this morning, and then you'll know. There will ultimately be a paper. This is going to be work with Stab Salel and Yetta site, Kimia Shaban, and the paper is mostly finished. And yeah, we'll get it out. Okay. Good. You say, okay, this talk is almost over. And here's always really the question. So what? Why do you care? Why do you care at all? And I've tried to convince you why you should care. And I want to give you two reasons, or two kinds of reasons. So why should you care as a mathematician about causal set theory? And what I hope I've been able to convince you is that physics asks interesting questions that you wouldn't think to ask strictly as a pure mathematician. That's one of the reasons I like doing things that are on the intersection of combinatorics and physics, and I hope that I've convinced you that maybe you should be interested in that as well. As to causal sets specifically, I've mentioned how it's not going to get you a lot of friends at the physics garden party, but the flip side of that is it hasn't all been worked over. So I think there really is still some low-hanging fruit here, and that's always nice. And it's also nice to be able to give back to the physicists, right? You prove some theorem, and then they actually care, and they're all excited about it. Now, I think I'm speaking to all mathematicians, but I could be wrong. So let me also say why I think you should be interested as a physicist. And the first is that the axioms that lead to causal set theory are extremely simple and extremely physically motivated. Even if they don't end up being enough, they should be there, it should be true. So I think that's a reason to study causal set theory. And the other, maybe more practical reason is, with renewed interest by mathematicians, then maybe there's a renewed possibility of progress. So I will get, yeah, thank you.
Any other questions for Karen?
Thank you for this talk, that was really fun. Can you tell us, can you say anything about probabilities you'll be putting on the edges of cup tree? Like, do you do the same growth process with using Q's and rates for generating the process this way?
I mean, I guess yes. It's a little trickier because you have to look at the paper. I mean, yeah, I think those are the short answer is yes.
Another question, you mentioned this connection with the longest increasing sequence of permutation and like the height of the ground capital set. So there are also like when you take like unions of longest like extra parameters, like does that mean something?
Well, I got it, but you just translate it over and see what it means. So I don't know what it probably means. And that's special to the 1+1 or 2-dimensional case, but still, 1+1 dimensions is a really great toy model. So I don't want to discourage people from working on 1+1, even though we've got a little bit more space here in the world.
I have another question. So the Rothschild, the Python function models had height pretty but very wide. But so you were saying that in physics it's more like the other way, like you are more time, but you don't have a lot of space.
Once it comes from transfer equation, I think for a good physics one, you want something in the middle somehow, right? Because yeah, you want a certain amount of time and a certain amount of space. Because you want something that looks, I mean, at least to some extent, it needs to look like something you could have done from the spring. I don't want to overemphasize that because you really want to be, you don't want to have to start with something, with a manifold. But just looking here at the world, like locally at least, we certainly look a lot like 3 plus 1 dimensional Causal space. And so should expect some properties that are something like that. You can also ask cosmologists what sort of things that they're expecting. You know, again, it should ultimately be telling you something about cosmology, and so yeah, they can tell you something about how wide it should be compared to how much time.
I was going to ask almost the same thing. If you said that there are some of these other models where you change the weights or you replace the root formula, and that they give you, well, you should have said broadly they give different types of graphs. But are there any that actually give graphs that are equally wide as tall, like that sort of thing? Like are there any of them at all possible?
I don't think anything is really a fully compelling answer.
So from the random graph theory, the posets look like those matrix, but from the physics, in the Causal theory, how do the posets look like? So you see like with.
Oh yeah, I didn't draw you one of these.
You mean like what is
Like
it?
what do the sprinkling ones look like?
Yeah.
I mean, I could get up like they're not super easy to draw. Because they have a lot of these things that are, because the covers will tend to be in sort of a hyperbola, they actually end up having a lot of fairly long links. Because if I'm here and then I sort of have a hyperbola of covers, and then but the same is true from every point, sort of have a hyperbola of covers. So when you draw them, you draw a picture of them, they've got a sort of messiness that comes from that. There's a lot of fairly long. I think that's not a very compelling picture. But if you go look at any survey of poset, you will see where they've done a sprinkling, and I'll just plot it for you.
And you can plot it in like the plane with your first one.
Well, it's 1 plus 1 dimension, we plot in the plane.
So for your last question is which book of Causal set you're recommend?
So my favorites is there's a survey by mathematician, which I don't know the name of off the top of my head, but there's a causal set. And you're very much a physicist, so this is a survey very much written for physicists. There's also one by these two, Graham Brightwell and I don't remember her name. Anyway, they have also written a survey that's more for mathematicians, something like causal set theory for mathematicians or something like that. It focuses a lot more on some of these probabilistic combinatorics perspectives on it, since that's what they do. So that one is maybe a good entry point for at least certain kinds of mathematicians, but it's not as comprehensive of sort of all the things that people think about from a causal set perspective. Whereas I think Sonati's paper, it's definitely a physics paper, but it's more complex.
Thank you, Karen.
Thank you.